Hello, let me introduce you to the Network Service Development Kit, which we are developing in scope of the SONATA European Research Project. From a very high level, SONATA proposes an integrated NFV service platform consisting of a management and orchestration or MANO platform on one side and a service development kit on the other side. So the MANO platform is capable of deploying virtualized network services on a virtualized infrastructure, and the SDK, the service development kit, on the other side is more to be seen as a playground or sandbox where a service developer can try out any new network services, can try out any updates or any new features in there, and gain confidence about the correct functionality before pushing it to the service platform side, where the service will eventually run in production. In this demo, we will highlight the several features of this SDK environment, and we will showcase the different steps that are involved when a service developer is developing a service into this SDK environment. So we will see how different steps, including packaging the service, emulating the service, together with configuration, testing the functionality, and also do a performance check of the service. So these functions are supported by the SDK environment and are demonstrated with several graphical interfaces and command line tools that can be used by a service developer. So after one or more iterations in the development flow of this SDK environment, the service developer should have confidence that the service is working as expected, and he or she can then create a service package and push it out of the SDK environment to the MANO platform where the service can be deployed in production. We want to highlight that the whole SDK environment is open sourced and freely available to download and install. We showcase here these 3 repositories and also have some instructions how to create a virtual machine that installs this whole SDK environment. I want to showcase one simple service now in this SDK environment. Other service examples will follow and will be made available through our GitHub page. The service showed here consists out of an OpenFlow controller connecting through a LAN network to an Open vSwitch, and the switch has an input and an output port where traffic flows. The SDK environment is installed in a virtual machine that's running here on VirtualBox. And once the virtual machine is booted and the SDK environment started up, we can browse to the web interface of our service editor. The editor requires you to log in with your GitHub account. Now for this demo I have set up a specific demo GitHub account. And once I am logged in, I will see that there's a workspace available where different example services are preloaded. I browse now to the network service that consists out of a controller and an Open vSwitch, and I have a look at the service graph that we can draw with this editor. And indeed we see different VNF nodes, different endpoints, and different links between all those components. So these are indeed the direct connections between the endpoints and the switch and the LAN network. We can also have a deeper look into the actual JSON format that's being used to describe the service and to compile the service package. So this is the same package format that's used to send the service to the MANO platform and to the emulator in the SDK environment. Now, to deploy this network service, I first need to start the emulator with a predefined infrastructure topology. In this example, I will load the topology consisting out of 2 emulated data centers connected by a switch. I load this here with a script. There's more documentation available on the GitHub repositories. But this Python script basically instructs the emulator to start up the required virtual data centers and the required virtual switches that define the infrastructure where this service can be deployed to. We have a graphical dashboard, so a web interface of the emulator that shows indeed that we have three nodes, so two data center nodes connected with one switch node in the middle. So let's again have a look on what has actually happened. So we have a service descriptor described here on the left side, two VNFs with two endpoints that needs to be deployed on an emulated infrastructure consisting out of two BOPs or two data centers interconnected by a switch. So once that the emulator is up and running and the service graph is ready to be deployed, we upload the service packet from the editor to the emulator. So and what's happening now in the background is that we have a customizable placement algorithm that places the VNFs and the service endpoints onto the available data centers in the emulator. And next to that, it also installs the traffic flows that direct the traffic from the endpoints through the VNFs. So these are the direct links between the input and the output port and the OVS switch. So this effectually implements service function chaining into the emulator. And we get a message that shows us the service has been successfully deployed on the emulator. And we can also check it in the emulator dashboard. So after a refresh, we see indeed that the VNFs and endpoints have been placed on one of the emulated data centers. And we can also see that each of the VNF interfaces, this information we will now use further for our next checks on the service. So up to now we have created a descriptor and a service package with the editor and deployed it on a virtual infrastructure in the emulator. Let's see now how we can test the configuration of this service. So if I double click on the OVS node in the dashboard, I get a terminal that gives me access inside the VNF. And I execute the command to see if the OVS switch in this VNF is actually connected to a controller. It appears not to be so. We see in the terminal output. So now I want to configure the OVS VNF in this service that it's connected to the controller and that it can forward traffic from one port to the other port. In practice, I want to test a configuration script that should also be used when the service is deployed in production. So this configuration script needs as input the IP addresses of the two service endpoints and the IP address of the controller. We find those back in the emulator dashboard and we can fill them into our configuration script. Next, we have a command in the emulator that allows us to execute this configuration script inside a specific VNF. So we execute our script into the OVS VNF, which configures the open flow entries in the switch and configures the correct controller IP address. So if we check again in the VNF terminal, we see now that the controller is connected. And we will further check if we can indeed send traffic from one port to the other through the Open vSwitch by accessing one of the service endpoints and pinging basically from one endpoint to the other to make sure that traffic flows through the Open vSwitch from one port to the other. So we see indeed that ping traffic is being forwarded. So at this stage in the demo, we have shown how to create a descriptor and a package of the service, deploy it in an emulator, test the configuration and the basic functionality of the service. As a final step, I want to show you how we can also automate functional tests of the service And meanwhile, while those tests are running and while test traffic is being generated, we can monitor different metrics. The actual description of which tests that need to be executed and which metrics that need to be monitored is centralized in one specific YAML file. This file is given as input to one of the SDK tools. The tool will parse the file, execute the commands of the tests, and meanwhile monitor specified metric. Every monitored metric in the SDK environment is exported to a Prometheus database, and we also have a Grafana framework that graphically displays the monitored metrics on a web GUI. The tool parses the file, executes the command, and generates a specific stream of test traffic that will load the VNFs in the server. In this case, we monitor the byte rate or packet rate of different VNF interfaces alongside the CPU and memory usage of the VNFs. So the functional test that we are running is gradually increasing the traffic load, and while it is doing that, the tool will do some statistical analysis of the monitored metrics. It will calculate the average and the confidence interval and plot these values on the graphs you see appearing in the smaller window. Once the functional test is finished, we see on one hand in the Grafana figures a timeline and see how each metric evolves in function of the time. On the smaller plot window, we see the result of the analysis, and it shows us an indication of the CPU usage that was needed to process the packet rate that was being given as input to either one of the two deployed VNFs. So if we have a closer look at the end of the test to the figures, we see that both the OVS VNF and the controller VNF have a significant amount of CPU load. This is because the test traffic we are generating causes many packet in messages to be sent also to the OpenFlow controller. And we see indeed that with this specific test traffic stream, we need more CPU resources for the controller than for the Open vSwitch itself, which gives an indication that for this kind of traffic the controller would be a bottleneck in the network service, consuming most of the CPU. You can also further examine the graphs to have an idea of which specific packet rate needs this specific CPU allocation, to have a detailed idea of the needed resource allocation for this network service. So let me summarize again what we have shown here. We have an SDK environment which has different graphical tools available to run through a development cycle specifically for NFV based services. If you want to have more details on this, you can check GitHub, you can check the website of the project for all deliverables and technical documents. I would say stay tuned and keep following us for more exciting services to be shown in this SDK environment.